The topic that we'll discuss today is binary operations. So let us start with the definition of binary operations. Let G be a non-empty set and star be an operation. Then star is called a binary operation on set G if A star B belongs to G for every A B belonging to G. Here star could be anything like addition, subtraction, multiplication, division, union, intersection, etc. Or we could define it as a function. Okay, binary operation is nothing but a function on G. This is how it's defined. So if we define a map as this and that map is a well-defined function, then we say that star is a binary operation on set of G. Let us see some examples. Example 1. Here I have taken addition and n cross n to n, and it is defined that ordered pair is taken to a plus b. Clearly this is a function, because if you take two natural numbers and add them, again you will get a natural number. So clearly this is a well-defined function. Hence addition is a binary operation on set of natural numbers, or we say that natural number is closed under that operation. Here n is closed under addition. So if you have a binary operation, now note this, that if you have a binary operation on G, then we denote it as G comma star. So here clearly addition is a binary operation on set of natural numbers, so we can write n comma plus. The second example is the map is defined this way: n cross n to n, ordered pair is taken to a minus b. Here this is subtraction, minus sign, and we would observe that this is not a function, and the reason is, in place of a if I take 2 and in place of b if I take 4, then by the definition 2 minus 4 will be minus 2, and minus 2 is not in this natural number. Okay, so you can see that 2 comma 4 does not have an image in this natural number. So subtraction is not a binary operation on set of natural numbers. Our next example, check whether the following operations are binary operations on Z or not. First one is a star b is equal to a plus b, where a and b are member of Z, integers. Clearly star is a binary operation on Z. The reason is, if you add any two integers, then you will get an integer only. So here the operation defined as a plus b is a binary operation on set of integers. Next is a star b is equal to square root of mod ab. A and b are member of integers. Here this is not a binary operation, and the reason is, in place of a you can take 1, in place of b you can take 2. So by the definition of this operation, 1 star 2 will be square root of mod 1 into 2, that will be root 2. Okay, so but square root of 2 is not a member of integer, so this is not a binary operation. Next, a star b is defined as 1 upon a minus b. Again, this is not a binary operation on set of integers, because if it happens that a and b both are same, suppose a is 2 and b is also 2, then 2 minus 2 will be 0, so 1 upon 0 is not defined. Therefore this operation on set of integer is not a binary operation. Next, a star b is defined as square root of a square plus b square. Again, this is not a binary operation. Why? Because in place of a I can take 1, in place of b I can take 2, and by the definition of the operation I'll get 1 star 2 is equal to square root of 1 square plus 2 square, that will come square root of 5, and a square root of 5 is not a member of integer. So again, this operation is not a binary operation on set of integers. Next, a star b is equal to a to the power b. Again, this is not a binary operation because in place of a I can take 2, in place of b I can take -2. Okay, so once we operate it, we will get 1 upon 4. If we operate this, we'll get 1 upon 4, and that is not a member of integers. So this operation is also not a binary operation on Z, because the operation to be a binary operation, you take any two element, after operating it, the elements should be again in that particular set only, but here it's not happening. So star is not a binary operation. Next is a star b is given to be LCM of a and b, and a and b are member of this capital this set capital A, which is given which has elements 1 2 3 4 5. Here in place of a I can take 2, in place of b I can take 3, and you'd observe that after operation you get LCM of 2 and 3 equal to 6, and clearly this 6 is not a member of this set A. Okay, so here you saw that you are taking two elements 2 and 3 from A, but after operating it, okay, you are not getting the result in the same set. So as this is not happening, if you could show for even a single pair that this condition is not satisfied, then that operation will not be called a binary operation. So here this operation star, which is defined as LCM of a comma b, is not a binary operation on this set. Now we have properties of a binary operation. First one is commutative law. So let's say we have a binary operation star on set G, then we would say that this operation is commutative if a star b is equal to b star a for every ab in G. Okay, so if you have a binary operation star on set G and this holds for each and every element, okay, then we say that the operation is commutative. For example, addition is a binary operation on set of natural number, okay, and it is commutative. This operation is commutative because if you take two natural numbers, let's say a and b, a plus b will be always equal to b plus a. Next is associative law. So suppose star is a binary operation on set G, then we would say that this operation is associative if this holds. You take any three element a, b, c in the set, and if this holds, that if you operate in this manner or in this manner, both the results should be same. If it happens, then we say that operation is associative. For example, here addition and multiplication of real numbers are associative operations. So if you take three real numbers a, b, c, any three real numbers a, b, c, and you operate this way once and you operate this way, you find that both the results are same. Same happens for the multiplication also. You take three elements in real number and either you operate in this way or this way, the result will be same. So we say that operation is associative. Next is distributive law. Here let star, and this is the circle, and we have put dot inside it. So we have taken two binary operations on non-empty set G. Then we say that this operation star is distributive over this if this holds for every ABC in G. Okay, so you take, suppose two operations are there, binary operations on the set G. Okay, two binary operations on that set G, and you take three elements, and once you operate this way and once you operate this way, if it happens that both are same, then we say that this star is distributive over this binary operation. For example, if we take R, set of real numbers, then multiplication is distributive over addition. You would observe that if you take three real number a, b, c, and once you operate this way, that is a into in bracket b plus c. This would be same as a dot b plus a dot c. Next is identity elements. So let star be a binary operation on set G, and let E be an element in G. So let E be an element in G such that this holds this A star E is equal to E star A equal to A for every A in G. So star is a binary operation in G, and if there is one element E in G such that this holds for every element in G, then we say that E is the identity element in the set G with respect to operation star. Okay. For example, multiplication is a binary operation on set of real numbers, and we know that 1 belongs to R. Okay, and you take any real number, this will always hold for this 1. Okay, therefore 1 is called identity element in R with respect to operation multiplication. For example, here q comma plus, that means addition, is a binary operation on rational number. 0 is the identity element. Why? Because you take any rational number here, you add with 0, again you get the same rational number. Okay, so 0 is the identity element with respect to this operation addition in the set of rational numbers. Q comma multiplication, here multiplication is binary operation on set of rational number, and 1 belongs to this rational number, and you see that you take any rational number, multiply with 1, again you'll get the same rational number. So 1 is the identity element. N comma plus, addition is binary operation, but natural number does not have identity element, okay, with respect to addition. Because suppose I take 2, what shall I add with 2 so that again I can get 2? We cannot have any natural number, okay, that will satisfy this. So addition, with respect to addition, we don't have identity element in set of natural numbers. Now n comma multiplication, that means multiplication is a binary operation on set of natural numbers, and here we observe that 1 belongs to natural number, and you take any other natural number, multiply with 1, again you'll get the same natural number. Next is inverse element. Let a star be a binary operation on set G, and E be an element, E be the identity element. Okay, so star is a binary operation on set G, and E is the identity element with respect to this operation star. And let A belongs to G. I'm taking an arbitrary element A. So we say that A is invertible. We say that A is invertible if there exists an element B in G, okay, such that A star B is equal to B star A is equal to A. Okay, so here the star is a binary operation on set G, is the identity element, and we take an arbitrary element A, then we say that A is invertible if there exists an element B such that this holds. A star B is equal to B star A equal to identity element. Okay, and we call that B is the inverse of A. Okay, and we write A to the power minus 1 equal to B. A to the power minus 1 means this is, it is read as A inverse is equal to B. Okay, inverse of A is equal to B. In fact, in this case, A and B are inverses of each other. Like here, if I say B is the inverse of A, that means A is the inverse of B. Okay, so in fact, they are inverses of each other. Now let us see an example. Here I have taken a set real number from where 0 is excluded. Clearly multiplication is a binary operation on this set. Yes, because you take any two number from this set, you multiply them, again you will get in the same set. So clearly multiplication is a binary operation on this, or you can say this set is closed under multiplication. And we also observe that 1 belongs to this set. Okay, and for any element here, this holds. Yes, so clearly 1 is the identity element with respect to multiplication. Okay, Now we observe that if you take any element A in this set, then you could also find one element 1 upon A, okay, in that set, for which this will be always true. A into 1 upon A equal to 1 upon A into A is equal to the identity, okay. So 1 upon A is nothing but the inverse of A, okay, and it is denoted as this. So inverse of A is 1 upon A in this case. So if I take 1, so if I take 2, okay, if I take 2 in this set, the inverse of this 2 will be 1 by 2. If I take minus 3 in this set, then inverse of minus 3 will be this, okay.